All right, today, as you can see, we're going to start some of our aromatic reactions. We had this on the schedule yesterday. It just said review aromatics and then continue with mechanisms. You have a problem evaluation. We will take care of that tomorrow. But we want to continue with this content. And one of the things that you will notice is that we handed out something like this. We'll get that when you return, because this is something that we want you to be able to utilize and make sense of with these aromatic reactions. Okay. And I want you to make note of this here. If there's a derivative on the benzene, it will direct the placement of whatever you're reacting that with. Now that is more so when we get over to this side here. So we can presume that these are going to react because without a catalyst here, even though these are double bonds, will these react readily, a benzene ring? Is it highly stable or highly unstable? It's a very stable structure. So without a catalyst, okay, then this just does not react. So that is totally different than perhaps something like that, okay? And again, we know that these alternating double bonds are in here. We just put that circle to illustrate that that's what's happening in here. So this reaction could proceed, even if you just put bromine on here, that will react without a catalyst. These all have to have a catalyst because benzene is just too stable. Okay, so what we see happening here is when you look at your flow chart now, okay, where do you see benzene? You could say, I see benzene all over the place on here. Yeah, so what that means is sometimes you're not always starting in the middle. But in this case, we're starting with benzene because there's nothing else attached onto here. And then what we see happening is we are adding on a halogen. So I always like to use a reference of a clock on here. So upon doing this, I would say somewhere around, I don't know, 5 o'clock on this benzene ring, okay? What is it that we see that's written in green there? It says halogens, okay? And then what does it say on the arrow? A metal catalyst, and that's what we've got here, iron chloride. So we've got a metal catalyst, and on this flow chart, it does use variables just like other parts of this does. R is just means an alkyl group, CH2, CH3, anything to that effect. That's what R means, okay? So then when we're talking about X at about 5 o'clock, does that X appear on the benzene ring with this reaction? Yes, it does. So somewhere along the lines, you would say that this reaction continues, okay? You got to draw them better than I do. Okay. So somewhere on this ring, you're not going to put X, because X is just a variable, because that could be bromine, could be chlorine, could be fluorine, any one of those, because those are all halogens. Okay. So somewhere on this ring, you would want to put what, do you think? Again, not X, because that's just a variable. Okay, so where on this ring would you like to attach that chlorine? Okay, so what that means then, this is a type of substitution reaction because really what is on the outside of all of these? Yes, there's hydrogens on there, but we don't write them in there because that circle is telling us not only is there alternating double bonds, but then there's also hydrogens on the outside, so we don't need to put them in there. The only thing we need to do is say, all right, there was a hydrogen here, but now we've chlorinated that, and now we've got, what would you guess that would be called? We don't want to guess. What would you tell me that would be called? Chlorobenzene. That's right, because we have a halogen derivative and a benzene ring. So we've got chlorobenzene. All right. So one of the things that we could say is that what was on here before that chlorine? There was a hydrogen. And how many of these chlorines did we use? Okay, so we could say that that's what we're illustrating here. One of these chlorines attaches onto here. It replaces a hydrogen, so we need to find a home for this one now. But if that hydrogen is gone now, which it is, what do you suppose it's looking for in this molecule? Yeah, it's going to look for a chlorine. So then you could say that this is what is left over, plus HCl. So the hydrogen was on here. It got replaced by the chlorine. So that hydrogen then now bonds to this chlorine. Okay? We will probably get into that a little further tomorrow because of this late start. I'm thinking that maybe we should do that problem evaluation on Thursday. Is there any reason that anyone's gone on Thursday?
All stay quiet practice.
Okay, is that right away in the morning?
Yeah, I think so. It's probably all day, so.
It's all day long. Okay. All right.
And Wednesday I'm gone for PT, so.
Okay. So yeah, so it really doesn't matter then. Okay. But we're not going to do it on Thursday.
So
Is that what I said?
we're going to save it for next Tuesday?
Oh, shoot. As I'm looking at that, today's Tuesday. Okay, yes, we'll just have it on Thursday. Yeah, I'm looking at the schedule and thinking of something else. So, well, gone. You just have to make up the time then. Because I don't know if we're going to get enough time to really spend our part of a review on here, especially when we're covering something new. Okay.
And this stuff won't be on.
This reactions is not on there.
This would be like a problem quiz 2 or something like
That would be later down. This is what we're focusing in on, what you would name that. Yep. Okay. So now, as we proceed further here, this is actually nitric acid. Okay. How do we know that? Well, our different acids are this one, hydrochloric. We've got sulfuric acid. We've even got phosphoric acid. But in this case, we've also got nitric acid, which is HNO3. So really, what you're doing is you're adding nitric acid, even with a sulfuric acid catalyst, because we've got hydrogen, we've got 3 oxygens and 1 nitrogen. So really, it's nitric acid, but it just makes more sense to write it like this. And here's why. Because when you look at your flow chart now, look for something similar to what we see here. Okay, at about what time on the clock? About 3 o'clock, okay? So straight to the right. So what we see happening then, this nitric acid, this will continue with this, I almost said reactant, no, but this catalyst. And then, oh, we don't want that color either. Okay. So according to your flow chart, or whatever, I just call it a flow chart. According to that, what is going to happen to this molecule? Okay. So then we've got 2 parts to it. We've got this one. We've got a triangle and a box. So which one, the triangle or the box, according to this chart, will attach to the ring?
Box.
The box does. So what we are doing, this is a nitro group, and I think that was on your worksheet that was handed out last week. So according to that chart, what is going to be attached onto this ring? You said the NO2 group. So where do you want that attached? Very top, okay? So therefore, got a little fruit fly flying around. I don't know if I got him or not. I don't think so. Anyway, so if this is a nitro group, which it is, what's this called? Nitrobenzene. Just like we chlorinated, we've got chlorobenzene, we've nitrated it now, and now we've got nitrobenzene. So do we have anything left on this side of the arrow?
Yeah.
We do. And what was on here before the nitro group took over? So if that hydrogen is looking for something to bond to, just like it did up here, what do we have left over in? We have an OH, which means we've got H2O. That's left over. Okay?
We get to use this thing on liquids.
Okay, this is, and that's, I would expect someone to to ask that. When you completed the A&P class, when it came to diagrams, we said do what first?
Oh, do it without first.
Okay, do the best you can without the word bank. Then you can utilize that later. Yes, so I would suggest that you try this. And I understand this is a lot to remember, but there's a reason that we want to state it that way, because if you're in here this year, chances are you're going to be doing this again either next year or 2 years from now. I mean, not everybody.
The only page we're working on right now is this one.
That's the correct one, yes. Okay. So, any questions on these two so far? We're good? Okay. So now, what is phenol? If we had to draw phenol, what would that be? That's a common name. It's also hydroxybenzene. Okay? So that means we've got our six-sided figure of benzene, and then we've got an OH group on there. Okay? And we are chlorinating that. Now this flow chart really isn't going to help you much. I know, right? We just heard someone say, yes. Okay? But you do have something that you can use to help yourself out, and that is this upper left-hand corner. Okay? When it says CH3, CH2, CH3, what does CH3 mean to you? That's a methyl group. And what is right next to it? CH2, CH3 is a what? That's an ethyl group, okay? Then if you went on CH2, CH2, CH3, well then we know we've got a propyl group, so you could keep right on going with these. But the idea behind that is that top line here is an alkyl derivative, okay? Then the next one down is what? Hydroxy, or OH. Then notice we have an amino group. And then we see that variable, or letter X, that means what? That means any halogen. Notice we don't put chlorine there because we don't know what reaction could be proceeding. It might be iodobenzene rather than chlorobenzene. Then the bottom one is a nitro group. So this is why we say this chart really isn't going to help you that much, okay? It does show you two different ways to make phenol on here. I mean, that would help you out because there are word problems that accompany this, okay? It might say, show a mechanism to make phenol. Of course, you would look at this and you see two different ways to arrive at the same point. But that doesn't help you once you get to there. What's going to happen when we see a halogen derivative on there? Well, I would say that's probably a pretty good question. This is where this is important. If there is a derivative on the benzene, or I could say benzene ring, it will direct the placement, we could say, of whatever's reacting on that. That's why this is important, okay? So what that means is, let's see here, what do we have? Let's say what, alkyl, I butchered that. So the top one says alkyl. Then doesn't say like it doesn't matter if I'm getting the order wrong. Then it's letter X, and then I think it's amino group. Doesn't say NH2. Something to that. Pretty close. Okay? So these top four will direct the traffic on there. What would you guess that those two letters mean? We just have not, we've used it, we just have not applied it in this manner yet. O and P.
Are they like words?
Yes. No. In other words, what would this mean to you? Oops, I did that wrong. I meant to put it down here. There we go. Say that again?
Ortho and para.
Yeah, that means ortho and para. Okay? So what these do is if these are already on the ring, like they are here, this is going to direct the traffic on what's going to happen on this end. So that means you don't just get one product, you're going to get two. So that is something very similar to what you see in the I don't know, I would like to say 830, when you get down into this corner, it's showing that this is going to split, because when you put an alkyl group, which is just letter R, an alkyl group is an ortho and para director. Then you might think there's actually one letter left that we have not talked about. That's a meta group. What do we have left on the bottom? So this then is a meta director. It's actually called a deactivator, really, because once you nitrate this, yes, it will proceed, but once you react that one more time, once these spots get filled, the reaction just halts because there's nowhere else to attach anything. We'll save the aniline for tomorrow, because we kind of had a late start today, and that's not your fault, but mine. So in this case, we know that this is going to proceed because we'll just presume, okay, this metal catalyst goes down here too. If it was up here, it's going to be down here. So we're going to have two products. The OH is not going to change because that was already on here. So then, according to this, we've got a halogen, or letter X. Where is the ortho position from that hydroxy group? And we haven't spent a lot of time on that yet, so it might be. Yeah, so you'd have, when you say the next one, that's correct, but you'd have to pick which side. Okay, so the right side. You could put it on the left, but you had picked right, and that's just fine. So that, excuse me, that's one product. So then what is your other product? Yep, it's at the para position, which means we're running out of space here and time. We would have plus. The OH is still in the same spot, and then the para position is where? And it would be down here. Okay. So if we had to name that top compound, what's that called? And you can use a common name, you can use an abbreviation too. Say that again. Okay, so ortho, and you don't even have to say the two. Because when you say ortho, you're saying that it's one spot away. That would be ortho-chlorophenol. Okay? And then our other product down here, para-chlorophenol. We did get that's the reason we wanted to do this, just to give you a little bit of perhaps a refresher on how to name these compounds. So we'll continue with some of these mechanisms and naming tomorrow. We'll have your first problem evaluation then on Thursday. Yes, you do have some papers that are due today. Make sure your names are on them, and we will catch up to you next time.